Okay, we have a fully working voice network, right? We got our dial plan, we've got Call Manager Express configured. At this point, I want to take a little sidestep to start talking about how that all works. Meaning, I want to look at the voice protocols itself. This is a little non-traditional way of teaching, but I love doing it this way. I don't like traditional approaches. Like when I first got into CCNA, probably just like many of you, is you get in and the instructor goes, oh, okay, what's a network? And you start learning about, oh, okay, this is what a network is. And then the next topic is usually like, okay, TCP/IP. And you start getting those architecture slides of like, okay, TCP/IP is a suite of protocols. And just remember, when you first start getting into this, the blank stare, you're looking at this slide with all these squares of UDP and ICMP and SYN and SYNAC, and you're like, huh? And so you just get lost for a while until you get to the configuration, and then you're like, oh, okay, this feels good. And then over the years, you start going, oh, I see why that model was pretty useful. Well, I like flipping it around. I like getting into the practical first, just like we did. Let's lay it all out and configure it, and then let's talk about the protocols that made that all happen, because I find it just feels better that way to say, oh yeah, remember when that phone rang? Yeah, that's why it rang. Or remember when, it's kind of like you have something to relate it to. So, what we're going to look at in this next little group of nuggets is the voice protocols that make it all happen. We'll look at the key protocols like RTP, RTCP, some of the streaming protocols, statistical protocols. Then we'll get into communication protocols, and that'll be our main focus. We're going to break these out and look at H323, SIP, and MGCP. Our primary signaling and communication protocols that make all of this happen. So we'll look at, from there, the voice over IP call processing stages, what it looks like when a packet is converted to voice. There'll be a little review from early on in the series, but then kind of fitting that together with how the protocols fit into that. And then we'll wrap up with the features and flavors of RTP. Now, my thought is that this will be a little shorter nugget just because it's going to be an overview. It's going to be a step into these protocols where the rest of the voice protocol little subsection I have here, we'll be breaking them down one by one. So let's start. Let's take a look at RTP. RTP is the real-time transport protocol. They snuck a little dash in there, so that's how it didn't become RTTP. It's a little t. This is the protocol responsible for delivering your voice. So we'll look at a complete end-to-end breakdown on the next slide, but here's how it essentially works. Let's say you're speaking into this microphone, conveniently attached to your phone. What's happening is the codec, whatever codec you're using, is converting that into data. So let's just say you're using G.711, like most things do. It's putting the sounds coming out of your mouth into a packetized format, that little G711 data component, and then it's sticking on an RTP header in front of that. Now, RTP is not its own layer 4 protocol. Like when you're looking at that little architecture slide of TCP IP, you don't see TCP, UDP, RTP, like RTP is its own little world there. It actually rides on top of UDP. So you might go, well, what's the point then? Why don't we just have the audio, your words that you're saying, coded in G711 or whatever codec, and put UDP? What does RTP add to UDP? Well, UDP is designed for simplicity and speed. It's virtually got nothing to it. It just puts port numbers so that you can tell what's what when you have data coming in. So you have these little port numbers that distinguish it. That's the UDP function. But RTP, well, it does a few things, but I would say the most important things is it adds a timestamp and it adds a sequence number. So it's almost when you think of sequence number, my mind immediately goes to TCP, right? That's where we have our window sizes, our sequence numbers, our acknowledgments. You remember all that? So it's like we're taking a little TCP and squeezing it in here using the RTP protocol. What that's there for is when you're communicating using your voice or your network. My brain is like, what is that called? When you're communicating across the network, you could have packets going all kinds of directions. I mean, you got load balancing happening, you got multiple WAN links, all that kind of stuff. So at the other end, when it all comes back together into one device, it may have all these packets received, and it's like, well, I need to put these back in order. Well, if you just had UDP there, it's not able to do that because it doesn't have any kind of sequence number, doesn't have any idea of what packet came first. So that's what this timestamp and sequence number adds in there, among other things. So that little RTP header is stuck on every single voice packet that you send. Now this is what you want to prioritize. This is the golden ticket. When we come to quality of service, which is the final section of this CVOICE series, when we get there, you're going to be like, oh, RTP is like, oh, I mean, that's your golden traffic that you want to make sure gets there, because if that goes bad, your call breaks up. It's often confused with RTCP. RTCP, think of these as like yin and yang. It's like you've got RTP, it's always there when you're communicating using voice, and then you've got RTCP, it's its little sidekick going right along with it. All this is a statistical protocol. It's there to track how things are doing on this voice call. It sounds, I mean, when you look at the name, you're like, oh man, RTP is the golden traffic. It's super important. So then you hear RTCP and you look at the definition, you're like, wow, this is like the control protocol. So if this is important, then this must control it all, right? Because you're thinking control, wow, that's a big deal. Not a big deal at all. This is like statistics. So if you're on a call, there's a little on the fly. Let's see if this will work. Let's say I bring up a call here. 1110. Oh, I'm calling myself. Hang on. 1111. There we go. And I will answer this call. Feedback. Stop. No. Mute. There we go. So I've got this call active. If you're ever on a call and you double tap this, you can actually see all of the statistics of that call. It's like, oh, hey, I'm using G711. I know some of you didn't know that. You're like, wow, that's cool. Yeah, just double tap that little guy right in the middle there, and you'll get the statistics for the call. It's showing, how much data has been sent. You can see not much is happening right now because everything's muted, but, what is the jitter, how many packets are discarded, and I can't scroll down. Can I use the arrow key? Yeah, there we go. How many packets have been lost for this communication. This stuff is this. Without RTCP, you would not be able to get the packet statistics. So let me ask you then, end that call. Let me ask you this. So when push comes to shove, and it's like the router's like, all right, I got two packets. I got an RTP packet and RTCP, and there's only enough bandwidth to send one. Which one do you think is more important? Bing, 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 bing. You got it. RTP. RTCP, if you lose a packet, it's like, okay, the statistics may be a little off. You may not get, but I mean, come on, not a big deal. So prioritize, not so prioritized at all. All right, now down to these last three. H323, SIP, and MGCP. These three protocols are focused on everything behind the scenes, the stuff that we take for granted. Like when I pick up my phone and make a call, somehow the digits I dialed had to get somewhere. Somehow that somewhere had to look at, oh, well, here's where it's going based on this dial here, and send a message that says, hey, Jeremy wants to call you. Somehow the phone on the other end had to receive a message that said, it's time to ring, and the phone starts ringing. That's the responsibility of all the three of these guys. These are our signaling protocols. Now, without these, nothing would be possible. I mean, this delivers audio, but without saying, here's where it's going, here's how it's going to get there, all those kind of things, it's just not possible. So think of these as like the core of what makes our voice networks work. Now, three of them, all geared around the same thing, which is call setup, call teardown, call maintenance if you need to put a call on hold. Those kind of things all happen during the call. So three protocols. First question you have to have is, why three? Well, when I first started teaching networking, it was a time when it was very common to see IPX, SPX, and NetBEUI, and AppleTalk, and DECnet, and all these protocols you just don't hear of anymore because everything is solidified on TCP/IP. Well, in the same way, voice over IP is still relatively new compared to the landscape as a whole. So right now we have these three, but eventually I have a feeling it's going to boil all down to one. But right now we have three. They each have their own niches, their own advantages and disadvantages. H323 is the patriarch of the suite of protocols here. H323 was designed long ago to do voice and video over ISDN connections. Now this was, back when ISDN, I don't know if you know this, how long you've been in this, but ISDN was supposed to be like the thing that changed the world. And from some aspects it did, to where people were saying, man, with that much bandwidth, I mean, we're thinking T1, 1.5 megabits per second, with that much bandwidth, I mean, the sky is the limit. What's going to be possible? And that's when H323 came along and said, I bet we can send voice and video over these data ISDN circuits, and they did. And H323, I still remember Windows 95 having a NetMeeting client on there and doing my first NetMeeting video share, and I'm like, wow, I can see you. It's like Star Trek. It was one of those kind of things. So H323, when I'm talking like that, you immediately get why this little image is sitting next to it. It is old. Or mature, I think is the better way to say it. It is an old protocol. That's not necessarily bad. I mean, when you hear old, you're like, oh, well, compared to technology, it must be obsolete. Well, let's talk TCP/IP, right? Old protocol. 1970s we're developing that protocol. So it's still in widespread use today. That doesn't necessarily mean it's bad. But back then, back when H323 was there, everything was kind of integrated. You had all of the signaling, the media, the audio. So it's just a very heavy protocol. There's a lot to it. It's not as simple as we would want a protocol to be. And that's where SIP came along, the Session Initiation Protocol. Now, you're probably like, so what's that image mean? Nothing. It just was kind of funny. I found that image when I was looking for things that SIP. So SIP is, just think of it as an evolution of H323. Instead of having this big, heavy protocol with all these standards associated with it, because back then that's what we needed, is kind of an all-in-one protocol, this one kind of separates it out, and SIP says, you know what? My goal here is to set up calls, to set up video sessions, to set up, fill in the blank. I am here simply to do what I do, and that makes it a very lightweight and customizable protocol. Now, SIP, one of the other benefits over H323 is it's very easy. Every time I see the word SIP, I think they should have named it like Simple Initiation Protocol, because it really is simple. The same people who created like HTTP, those kind of standards and those kind of messages, created SIP. So when you're online and you go to a web page that doesn't exist, what error does it give you? You remember? It's 404. It's like, oh, page not found, 404 error. Those are all HTTP codes. And since the same standard body created SIP, they said, well, let's use the same one. Like 4xxx is client error messages, 5xxx is server error. I mean, same kind of error codes, very clear text, very well known. It's very easy to understand. Whereas H323 was built on the old ISDN standards. So you do a debug of that guy, and you're like, what? What did it say? And it's like code 00AB9653. Google 00. How many 00? So it's one of those kind of games with H323. Now, both of these are considered peer-to-peer. This is a big, big thing to know. Peer-to-peer. What does that mean? Well, think back to networking foundation, or I guess I could say server foundations. When you get into servers, I mean, network is just a means to an end. We're really trying to share resources. So in a traditional peer-to-peer model of all of these computers, you've got your accounts that you have to create on each one of them. Your user accounts, if you will. So you eventually can scale that only so far, and you're like, okay, that's it. We got to have something central. We need a server to where all of our user accounts exist down here in one centralized place, and all these guys report and get their information from here. So this uses a peer-to-peer model, which is interesting because each one of the endpoints, each one of the devices participating in this protocol can have a lot of intelligence associated with them. That's why I can go on my voice gateway, for example, and put in a full-blown dial plan using up to 2 billion dial peers, right? Remember those little tags on there? Not that we would put that many, but you could create your full dial plan on there, and this guy becomes kind of an all-in-one intelligent endpoint that's able to participate using H323 or SIP. One or the other. Now you can use both, by the way. This one can maybe talk to one peer using H323 and one peer using SIP. And something worth mentioning is that on Cisco routers, H323 is the default. So when we were doing all the dial peers, remember early on in the series when we were doing the dial plan, setting up dial peers, those all use H323 signaling. we have to actually convert them over to SIP. But each one of these can be a full, intelligent, peer-to-peer endpoint. And that's where MGCP comes from. And you're like, what are you trying to say there? It's Star Wars, He's a Sith, and he has to report to the Sith Lord, who gives him his instructions, who is responsible for telling him what to do. That's my loose link to that. That's what's special about MGCP. These two are kind of just like evolutions of each other. It's like, here's the older one, here's the newer one. It's the next generation. This one is completely different. This is a client-server architecture. What that means is we have a centralized device. Actually, I'll just use this model. We have a centralized device where all of the intelligence exists. And I say device, but it could be set of devices. We can have redundancy with this. And all of the gateways report to that device to get their intelligence from there. So the beauty of MGCP is in its simplicity and centralization of setup, to where I could here's one example. One of the big thing that's happening now is you get hosted voice over IP. To where you have a common carrier, let's say, sitting right here, right in the middle, a service provider of some sort, who's connecting to all these different clients and hosting their voice over IP for them. So they don't actually have to have staff that supports their voice over IP system. It's all supported from here. Well, I've seen this a lot of times. For example, Quest, now CenturyLink, in our area, had many gateways at my customer premises, people that I supported. And I would come in and they would say, oh, we're locked out of that router. And, anytime I hear I'm locked out of that router, I'm like, oh, let's recover it then. So I would get in, and sure enough, CenturyLink or Quest was using MGCP to control all of these gateways. So that way, they could create the dial plan centrally at their company. And they could push it to all these devices instead of having to put a full-blown configuration on each one of these, so all these gateways would have the intelligence. So that's the advantage, is it's all centralized, it's all very, very scalable. Drawback? What happens if one of these gateways lose their connection? Well, it's like you lose your brain. It's like the old mainframe dumb terminal right there. So if it's just an MGCP configuration, then this guy has lost his intelligence. He's not able to make or place calls anymore because he's lost connection to the server. So how do we prevent that? Well, that's where it gets kind of funny. That's where you go to SRST. Survivable remote site telephony. And what SRST really is, I mean, if you peel back that friendly fun name, it's putting a backup H323 or SIP configuration on there in case MGCP goes down. Now, that may lead to the question, you're looking at it going, okay, so MGCP centralizes it, but I have to put a backup H323 or SIP configuration on there anyway. Why wouldn't I just put an H323 or SIP configuration on there to begin with? Good question. It is, and I would say that is a valid statement, but most of the time these backup configurations are very simple. They're just like, hey, here's your functionality. Like, here's an FXO port, 9T. That's your backup configuration. Somebody dials 9, and then any number of digits that goes out this port, that's what we fall back on in case MGCP goes down. The last thing I want to do is put all of these pieces in place in a voice call processing scenario. Where do all these protocols fit? How does it all happen? Some of this we've talked about, and I'm not going to go into the same depth I did early on in the series, but never have we put it all in one place. So giving some devices identities, let's say this guy's router 1 and router 2. I've got a voice over IP handset and an analog handset over here on the left hand side. So we'll just say this guy is a CME router. CME. So let's look at the analog handset first. He lifts the handset and gets dial tone. Now what's generating that? That would be the DSPs inside of this router, the digital signal processors, because that analog handset, I'm looking at it in front of me, it's yellow, all yellow because it's all aged and nasty. All it is a bunch of wires, a speaker, and a receiver. It doesn't have any power in itself to do this kind of stuff, so it relies on the DSPs inside the router. Now, as soon as I make a call, this guy is going to signal using whatever protocol you've configured, throw SIP, throw H323, it's going to signal to the other device saying, hey, I have a call for you, and establish that call. Once it does, that's where we begin sampling. So I'm talking on the phone, I'm going, hey, Roger, how's life? Meanwhile, the DSPs inside of there are going, okay, I'm taking that analog waveform, kind of draw that up against, the little wall, going across there. It's taking samples of those, and if you remember our good old Nyquist theorem, that's going to be 8,000 samples a second. It's like a little Jinsu knife going, chopping all that up. From there, it's doing quantization, essentially translating those samples into a number, a value of some sort, and then encoding it using whatever codec algorithm you're supposed to be using. For instance, G711, you have that U-law or A-law. It uses the encoding standards, PCM, those kind of things, to where you're encoding it in as a binary number. And if you are using a compressed codec, that's where it's going and smooshing it down as well, so that you are saving bandwidth. And it could, there's let me just put it this way: there's many ways to smush. That's why there's all kinds of different codecs that are out there. From there, we now have at that point our payload. This is the, if I said it really fast, this is the hey Roger. I'm talking really fast. 8,000 samples a second. So I managed to squeeze that out in 1/8,000th of a second. And that's where we squeeze it in the packet. Now, voice over IP encapsulation is where the gateway realizes I've got to send this over a SIP connection, over a data network. So I'm going to add on our RTP header, giving me my sequence number and timestamp. I'm going to put the UDP header on there, and then from there, it's just all IP addresses and MAC addresses that get added to the front. Our normal encapsulation. Get the CRC or frame check sequence slapped on the end there, and now you have a complete packet. Shoop goes across to the other side, network transport, and then from there it gets de-encapsulated. It says, okay, UDP, RTP, let's put them all back in the right order. Make sure that they all fit together into one seamless stream. Decodes the information inside of there, whether it's a compressed codec or, essentially is taking that codec and looking at what it's saying, and then it does modulation. And that's where we convert from our binary numbers into sounds that somebody would hear on a headset. So that's kind of an end-to-end flow using this. Well, using the technology that we've talked about so far. Now, the reason I added a voice over IP handset up here is because when you go with a voice over IP handset, the DSPs move from the router, not physically, it doesn't move, but the DSPs are actually inside of the phone. So this, and sort of this all happens within that device. And I say sort of this because it's the one that actually kicks it onto the network. This phone doesn't have anything to do with an IP-based network. So by using these, you really have distributed all of that processing and voice encoding and all of that to all the different devices on your network. Okay, I said the last slide was the last slide, but I forgot about this one. So let's talk just a little bit more about RTP, because this is the only place we're going to talk about it. It's such a simple protocol. There's no sense in dedicating an entire nugget to it. There are more flavors to RTP than just RTP. And remember, RTP, its goal is to deliver video and audio streams over data networks, and adding timestamp information so that the devices, even though they're using UDP, can put them all back in order and know the relative time they were sent. There's a flavor known as CRTP, which stands for compressed RTP, but it's not really compression. They just say that because compression describes the essence of what it does, which is make it more efficient. On lower speed connections, and this is the key here, think T1 speed or less is considered lower speed. You want to consider using this because inside of every packet, let's say here's my hi Roger, right? My voice, hi Raj. You have the RTP header, the UDP header, the source IP, the destination IP. I mean, all of the normal stuff that you're seeing. Well, all of that data totals up to about 40 bytes per packet. And I say about, but actually it's exactly 40 bytes per packet. And we know that because all of the fields inside of those headers are fixed. I mean, the source IP address is so many bits of information that never changes. Same thing with the destination. So what CRTP does is take all of the redundant information in those headers and strip it out. So first off, this is something that both routers must agree upon, because otherwise one of the routers is going to be like, what are you doing? So what's redundant in a conversation? Well, it's always coming from the same source IP address, going to the same destination IP address, using the same source port number, going to the same destination port number. So really, I mean, if you think about it, almost everything in those headers is redundant, and that's why compressed RTP takes our 40 bytes down to 2 to 4 bytes. Yeah, that's pretty amazing in the compression ratio, because it's not really compression. It's like stripping it out. I don't know why. For years I've been talking about this, and every time I talk about this concept, I just think about gutting a fish. That's really what compressed RTP is. You know, you just kind of like dump out all that stuff you're not going to eat, and then you just have the good stuff, the stuff that is tasty, all left over. So same kind of thing here. It's not that. Anyway, that's where the analogy breaks down. It's not tasty, but only the stuff that is changing, things like timestamps, things like sequence numbers, are still left in that header. Everything else is stripped out. However, you might say, well, why is it just on less than T1? Well, this does cost quite a bit of processing power. So it's not something you want to do on a high-speed connection, because it can bury your router. It's really, I mean, the router's taking all these thousands of packets and stripping out information, and then adding it all back in when it gets to the other side. So next one, secure RTP, SRTP, provides encryption, authentication, and integrity services, which really is integrity. But what this does is make sure that your voice is secure. Now you might say, well, can't you do that with a VPN? I mean, can't you, if you've got remote phones? Well, first off, on the normal network, is it safe to trust that it's secure? Well, maybe. Depends on your standard and your network. And when I say normal network, I'm talking, 2 phones on the same switch. Do we need encryption for calls between those phones? I would say it depends. Depends on how warm and fuzzy you feel about your internal network. I would say most of the time, this is considered safe. Where you get into the danger is when you've got and it's not a WAN link, but you've got this guy connecting from outside the network. Maybe he's a remote office. Maybe he's a telecommuter with a IP communicator on his laptop roaming around. That's where you run into the challenge. And so you might say, well, why not use a VPN? Does that work? It does. I've done a lot of voice over IP over VPNs. Challenge with VPNs is it's not as efficient. Not as efficient, nor is that VPN as flexible. Not flexible, because there's not every phone out there that has, as a matter of fact, very few phones out there actually have the ability to do VPNs from the phone. However, almost all the phones out there have the ability to do secure RTP from the phone. So if you want to have your telecommuters running around with a router that they have to plug in front of their phone, then sure, a VPN works great. But if you just want to be able to have the flexibility of moving phones around, then that's where secure RTP comes into play. It focuses on just encrypting that audio without all of the other stuff that VPNs typically do around it. So it's more efficient, it doesn't send as much bandwidth essentially as a VPN, and it's more flexible. Last one is VAD. VAD allows you to save bandwidth by suppressing the sound of silence. Sound of silence happens when somebody sighs, when somebody takes a breath, when somebody is quiet on a phone call longer than just a few moments of time. Now, you might be like, well, I mean, if you're on a phone call, are people ever really quiet? Actually, yeah. There's a lot of silence that can be stripped out between two people. It's not just the deep thoughts, when somebody's silent, thinking about something. It's not just those times, but I mean, there's a lot of little pieces of silence that can be cut out. Matter of fact, on average, Cisco says, if you take a T1 worth of calls, which is 24 active calls, on average, you will save 35% of your bandwidth by using VAD. Now that's on average, and that's using 24 calls because it varies based on the callers. I mean, you can imagine that someone like me who talks all the time, would probably not get the 35% bandwidth savings on my call versus somebody who often pauses and deep reflection. I mean, he makes up. He's like 70% bandwidth savings. He makes up for my 1% of bandwidth savings that I would have using a VAD scenario. Now, with all this being said, Cisco documentation constantly points to the fact that you should not calculate that in. That should just be bonus bandwidth, like, hey, we get it. It's not something where you can now say, great, I'm using VAD. I'm going to over-provision all of my stuff by 35%, because Cisco says you can't always count on it. It's kind of a rough average, but it's just bonus bandwidth that you get back. So those are our voice protocols at the core. We've been using them this entire series. It's been behind the scenes, and now it's time to pull these mysterious actors out to the front and say, here they are, let's introduce them and tell you what they can do. So in this nugget, our focus has been primarily just an overview of the players, an overview of the actors in our scene, and then a focus in on RTP, because again, beyond what you saw right there, that's all there is to RTP. What we're going to spend the rest of this little subsection on, this voice protocols, is taking each protocol one at a time, H323, SIP, and MGCP, and breaking them down and showing you what their advantages are, what they're capable of, and then a mindset behind the architecture of setting them up. I hope this has been informative for you, and I'd like to thank you for viewing.